Well, today during our open journal and during the last few minutes of the Community Spotlight Gumbo Edition, you may recall my paraphrasal of E.O. Wilson's, the famous evolutionary biologist. And, well, allow me to reiterate that. Quote, "Ideas emerge when the world is studied for its own sake," end quote. That's the purview of basic science research. Man, that's what I call what it's all about. Basic science, that is. For as the good doctor went on to later state, and I'm paraphrasing here, for every problem, there's a phenomena, entity, or species with a potential solution, yet never before imagined. That's the solution, that is. I guess they call that thinking outside the box, exploring new horizons, see where the evidence is and where it takes you. That's what real science does in every discipline of scientific endeavor, from biology to physics to computing. And, well, actually, these disciplines cannot stand alone in isolation, but are connected in a single body of knowledge. But for the sake of reducing it into a conceptual framework, we've, well, separated this body into separate disciplines, hence what I mentioned: biology, chemistry, physics, mathematics, computing. And, well, today we're going to take a look at a new and exciting way of computing that's totally different from today's standard of digital or linear computing, and explore the concept of nonlinear or analog computing that actually derives its inspiration from biology. In short, it's sonic or vibration-based and relies upon coupling oscillations, from which the basis of this is, well, it's non-Boolean logic. So that's what's on tap for today. Good afternoon. You're tuned in to Welton Shawn on KPFT 90.1 HD3, broadcasting from deep in the heart of Montrose, just left of downtown Houston. I'm Mike DeLeonardis, bringing it to you, and I want to thank you for listening. And so today we're going to take a peek inside non-Boolean computing, or associative processing. See how it works, what it's made of, what may be its potential, and how it differs from today's standard of digital logic or Boolean computing. And on the line, I have two experts in the field who are actually on the frontiers and may be establishing the fundamental laws on how to do this. So, from Georgia Tech University in Atlanta, Georgia, I have on the line with me Dr. Arijit Raychowdhury, and I kind of slowed that down and so semi-butchered it, or maybe butchered it in total. But Dr. Raychowdhury, I want to welcome you to the show, and it's a great pleasure to have you. And next up, thank you very much. Thanks for being on.
It's my pleasure.
And at Penn State University in University Park in Pennsylvania, I have Dr. Suman Datta. And Dr. Datta, I want to welcome you onto the show as well. It's great to have you guys, and it's great to, it's going to be, just flat out, it sounds like some pretty cool stuff that you're doing. And both of these guys are professors of electrical engineering. They're scientists in electrical and materials research. And so I know Arijit does, and I just had to say this because, you know, VLSI sounds like a really cool acronym, so I have to just say what it is, very large-scale integration, and that deals with digital design and probably, you know, what I remember from, you know, actually, and this is actually way back looking at little pictures of, I don't know, 8086 pre-Pentium processors. I'm not sure. Maybe they were considered very large-scale integrated systems. But I want to welcome you both on the show. And, well, I guess first up, we want to explore exactly what this is. My assumption is that well, this is, and from what I read on the little news blurb that, you know, basically described your research, is that this deals with vibrations and coupling oscillations, and these couplings of oscillations, which somehow match as the basis for this non-Boolean logic. And, well, I'm just going to leave it at that and open it up for either one who wants to go first to describe this.
Sounds pretty good, Mike. This is Suman joining in from Penn State. Glad to be on your show. So I'll take the first stab and then lead it on to Arijit to describe the remaining. So as you said, clearly this new discovery that we reported in the Scientific Reports Journal from the Nature Publishing Group, we were quite excited. And as you said, that we are dealing with oscillators, which are very different from transistors that's used in modern microprocessors like in your laptop or your smartphones or in these big servers out there in the cloud. So this is definitely a very different form of device. The physics is different, and obviously it's a non-linear system, as you already mentioned. So for general viewers, I just want to quickly set the stage of why we're doing this thing. Why is National Science Foundation and Office of Naval Research, which is part of U.S. DoD, that's funding this research, and start with that. So this is a problem we started working on about a year back, and it started basically with as you said, a fundamental quest for looking for something alternate, I won't say better, but alternate to our transistors, which we have used for over 50 years since the discovery in Bell Labs out on the East Coast 5 decades back. Transistors obviously are extremely powerful, and they follow the so-called Moore's law, and we're able to still, the industry and the academia alike, they've been able to shrink these transistors. That has given rise to VLSI, the very large-scale integration that you talked about. Actually, we call it ULSI, ultra-large-scale integration. Computers are getting cheaper and cheaper, and I think most of your viewers, listeners, are using that technology. Going forward, I think we are seeing not only computing being a mainstay for our digital economy, but we are going to see more features to be added to the so-called computer. So, for example, folks are already thinking about integrating sensors on top of these computing machines. For example, people are already thinking about whether we can make our computers, see us, process visual images, or sense our touch. For example, you see these robots, Japanese robots that are helping the old people, and processing storing those kind of sensor information, which are fundamentally analog, because that's the analog world we live in, requires a lot of computational resources if you were to do this thing purely digitally. So this was our inspiration, actually, to start looking for other alternate modalities through which and come up with a device, let's say, which is very different than a transistor, a device that is more suitable for doing analog signal processing.
Well, that's a good point to stop right there and describe the difference between. Well, I'm looking at this material, vanadium oxide, or it could be titanium dioxide. I don't know, but either one. But I as a very scant knowledge of semiconducting technology. Well, if you and I'm remembering old schematics. If you apply a charge to the middle of a transistor, well, it conducts. If you don't apply a charge, it's an insulator. And this sort of oxide that this in this news article they called a wacky oxide. What is wacky? I'm kind of wacky myself, but anyway. It basically it apparently does the same thing. So I was wondering if you could kind of make a parting here, weave a difference between what transistors do and what the particular substrate you're working with does.
Sure, definitely. So silicon is what we use in order to make this transistor that you just described. That it has three terminals: source, drain, and gate. And we apply a positive charge to the gate, and it turns on the channel, and we turn the transistor on. And that's the one state, the state of one. We apply a negative charge or zero, and we turn it off. That's the zero. That's the 0 and 1. The switch that toggles between these two states. So that's binary operation. The material that we are dealing with is vanadium oxide. We call it wacky oxide because typically when you describe oxide to students or to a common person or even to many folks, they think that it's insulating. It's something that has that is always off. It's very difficult to pass a current through an oxide because it's the other name for oxide is insulator. We always use that term. What makes this vanadium dioxide a very special insulator or an oxide, aka wacky oxide, is because it can actually, under the influence of a stimulus, in this particular case, electric field or electric current, it can change phase from going from an insulating state to a completely conducting or a metallic state. So this is a material where both insulating and the metallic properties are there, and they're hiding there, and so it's not a simple, usual vanilla flavor oxide in that sense. And just moving on, if you just keep the thought that a material that under some circumstances, is insulating and then it's conducting, but that seems a little bit like our silicon transistor. Okay, so you apply a voltage and you turn it on, and then you apply a negative voltage, you turn it off. But this does a little more than that. Under certain special circumstances, and this is what my graduate student was able to demonstrate in our lab, is that under special circumstance we can actually stabilize both the metallic, aka conducting, and the insulating, aka non-conducting states within this same material at the same time, and just with a little bit of perturbation, if you just apply a DC voltage, what we do is we make this material sort of metastable, so it cannot make up its mind. It's wacky. It tries to go to the metallic state, then something brings it back to the insulating state, and then again it goes back to the metallic state. So this is what we were able to see in our lab. We set up these sustained oscillations, and we were able to make an oscillator. And when we were able to make an oscillator, we said, okay, this is cool. We can publish, just basic science, but we want to do something useful. And this is where we enjoyed talking to Georgia Tech folks, particularly Arijit, and Arijit can describe to you how we were able to actually couple these two oscillators and start thinking about brain-like computing.
You know what that reminds me of? And phenomenologically speaking, it kind of, when you said at the same time, I kind of, what popped into my mind was this qubit phenomenon of quantum computing, and it almost sounds like well, I'm going to take a leap here. I'm going to go out on a limb, but that certain sorts of quantum phenomena are like oscillatory phenomena, and that's I guess that's the similarity that might be why I got that intrusive thought. And I know this is kind of funky, but any thoughts on that?
Arijit?
I don't know. Arijit, are you there? Did we lose you?
Yes, I am here.
Oh, okay, great. I was going to give you a call. I don't know if you caught what we were talking about. I'm looking at the board and all the buttons are right, but this is the man behind the curtain in the Wizard of Oz, but we're trying our best.
Yeah. I couldn't follow. I mean, I can't hear Suman, so I couldn't follow it.
Oh, you can't hear Suman?
No, so I couldn't follow the discussion that you guys were having, but I guess you were discussing something with him.
Oh, that's the beauty of technology. And we've got a 30-second delay on our online listening thing, but maybe you can catch up. What he was talking about was the properties, what Suman was talking about, I suppose, was the properties of vanadium oxide and how it allows the signal to oscillate in a way that is kind of simultaneous in state-wise, and I was asking him, it kind of reminded me of the qubit phenomena of quantum computing, and I was wondering if you could kind of get the gist of that. I know that's kind of clumsily explained, but I guess it all boils down to the properties of how this particular substrate, vanadium oxide, behaves and how it allows to do what it does as far as oscillatory behavior.
Yeah, so that's a good question. I don't see a direct connection between this kind of systems and qubits, for example.
Sure.
There is definitely a quantum phenomenon going on within the material, and the material, when you connect it correctly through electrical means, would produce an oscillatory response. But once we have these sustained oscillations, and we can actually build multiple of them and couple them appropriately so that they produce what are called synchronized coupled oscillations, I think the system is, at that point in time, the system is not using quantum information processing as the basic computational model. Instead, the basic computational model that we are pursuing is something that I already mentioned. It's something like associative memory, where you try to do pattern matching or even image recognition, things like that, using the inherent dynamics of the system. Mm-hmm. The whole phenomenon of synchronized oscillations actually isn't very new. I mean, it goes back all the way to 1600, I think 66, when Christian Huygens, he was a Dutch physicist, he first noted that if you have two pendulums which are suspended from the same bar, they kind of synchronize in their oscillations with, and they kind of start swinging with the same frequency and they lock in phase. So that happened more than 250 years ago, and researchers from all fields, all disciplines, biologists, chemists, physicists, mathematicians, have been studying these synchronized oscillations everywhere, in nature, in physical systems, and so on. So understanding the exact dynamics of these kinds of oscillatory systems is actually non-trivial. And what we are trying to do is we are trying to understand when these small oscillators made of vanadium dioxide, when they couple with each other electrically through what we call resistors and capacitors, then as they keep on oscillating, they kind of lock in frequency, meaning thereby that although they may start off with slightly different frequencies, when you couple them all together, they kind of synchronize with each other, and they harmoniously will keep on oscillating with the same frequency. At the same time, the phase relationship between these oscillators, which is essentially, if you think about, again, in terms of a pendulum, if you have two pendulums which are coupled to each other, then they are essentially swinging with the same frequency. But when one pendulum is at the far extreme left, the other pendulum can be at the far extreme right, or right in the middle. So that essentially defines the phase difference between the pendulums. So although they may have the same frequency, but their phases may be slightly different.
Yes.
And very interestingly, we see that when these large systems of coupled oscillators are appropriately coupled, you can get phase patterns out of them. So if one oscillator is, let's say, at the high, the other one is at the low, or somewhere in between. And when you have these very large systems of oscillators, they create very interesting phase patterns. Mm-hmm. So think about it this way. Let's say I have a system of many oscillators, let's say 100 oscillators, and I train the system so that they create unique phase patterns. So out of these 100 oscillators, you can have many phase patterns that you can potentially create. And let's say I could somehow create all these different phase patterns, and I could make some of those phase patterns stable, meaning thereby when I let the system oscillate on its own, it will eventually settle down into one of those steady-state oscillations, meaning thereby that it will get captured into one of those steady-state phase patterns. Uh-huh. So when I have an unknown input which comes in, depending on which of these phase patterns is the closest to that unknown input, the system will eventually settle down to that particular pattern of phase oscillations.
Okay.
So if you think about it this way, that there are many energy minimas. So we call, again, scientifically speaking, these are energy minimas that you can create. And if you have an unknown input that comes in terms of phase relationship between oscillators, then the system will always try and identify the closest energy minima and settle down at that energy minima. Mm-hmm. So let's say I could have 100 different phase patterns out of these 100 coupled oscillators, and let's call them 1, 2, 3, 4, and so on. So if I have an unknown input, which is, let's say, 2.2, then it will find that the phase pattern 2 is closest to it, and it will settle down at that particular phase pattern. So you can think about it as a very simple and naive way of doing pattern matching. So when I have an unknown pattern and I have a dictionary of known patterns, then the unknown input will always take the system towards one of those known patterns and eventually settle down into a known pattern which is the closest to the unknown pattern. So that creates a very simple way of doing what we call template matching, or matching between an input and a dictionary of knowns.
So if I were to ask the question, it's not so much phase synchronization. It's more like, and I guess I'm just borrowing from the article, phase coupling. No.
Yes. So coupling is essentially a way of by which the individual oscillators will talk to each other. So if I have two oscillators which are not coupled, they are uncoupled and they are isolated, then they will have their own characteristic phase and frequency. But as soon as we couple them, they go through a mechanism of negative feedback, by which they synchronize with each other and they couple with each other and they create this steady-state phase patterns. So this is something that we see in nature all the time. Particularly, my favorite example is that of fireflies. So if you look at fireflies which are firing at the same time, and if you bring another firefly into the system, you will see that initially it will fire randomly. It will not be synchronized with the rest of the colony. But eventually, if you just let it be, it will identify when the rest of the fireflies are firing, and it will catch up with them. And eventually, over a period of a few cycles, you'll see that all the fireflies are glowing at the same time, and they have locked in phase and frequency. The same thing we see in nature with crickets when they are chirping. So if you listen to them carefully, you'll see that they're all chirping synchronously and in harmony. And how do they do it? They are like all individual oscillators who have coupled with each other, and they have created a system where they are all locked in phase and frequency. And we can borrow from that same analogy, and we can build electrical systems which show very similar behavior. And what we are exploring is how to use this behavior into doing something useful for us. That is computation.
You know, and I'm going to leave this out there for either of you, and I suppose we'll have to create an order so that you can't hear at the same time simultaneously that, you know, you're talking, but I guess I recommend if you got a computer on, just click our PHP player and go to HD3 so that you know what the other is saying. That is Suman is saying or Arijit saying at the same time. But it's a fascinating aspect of this phenomenon because obviously. It's biologically inspired, and what's very interesting is this phenomena is beginning to be looked at in certain areas of molecular biology. Just last week, I talked to a fellow over at the University of Glasgow, and he's looking at the way a particular protein, lysozyme, specifically behaves, and he found out that at a certain frequency and during a certain point, and the point tends to correlate to its enzymatic activity, is that, well, it expresses a certain frequency somewhere around, I guess, in the picoseconds. Well, the time frame of the activity is picoseconds, but a certain vibratory pattern correlated with its oscillation. And I believe I discussed with both of you that. Earlier in the year, I talked to a particular gentleman over at MIT, working at MIT now, Anirban Bandyadape, and he is also doing the same kind of work that you're doing, and we were discussing the aspect of tubulin behaving in the same manner. So apparently this biological phenomenon is beginning to be looked at the molecular level and beginning to show signs because of the increased advances in instrumentation to look at this stuff. And I guess first up, let me ask you, Suman, is this a quantum phenomena that is just beginning to be realized in biological entities at the molecular level? And a two-part question, I guess. And so are you taking that and applying that to computational aspects?
Sure. So I think at the end of the day, being a physics, solid-state physics person, the very origin of these oscillatory behavior or any kind of collective behavior is related to in solid state. It's related to electron-electron interaction. In the case of biology, it's related to movement of ions, and the cell signal. I'm not an expert on cell signaling, but we do talk to folks in particularly neuroscience, trying to understand how these kind of collective phenomena, these kind of synchronization of different oscillators or different neural oscillations, how do they actually help us in executing certain cognitive tasks. Definitely, there are a lot of similarities. We, unfortunately, right at this point of time, we do not have an artificial hardware, where we can directly take a vision algorithm, that the neuroscientists are, let's say, trying to come up with and directly map it on to an existing hardware. So the answer to your question in two parts. One is at the fundamental atomic scale, are there quantum interaction at play? So the answer is absolutely yes, because just the sheer size, when we go down to an atomic level, classical physics breaks down, so we have to apply certain quantum capability. But it's not just quantum mechanics. One of the things that we are exploring with some of our theorists is just quantum mechanics plus what we call many-body interaction. So this is not single particle quantum mechanics that's at play here, and that makes the problem really, really much more complex. And that is something we are talking to our theoretical physicists and transport theorists to help us with. Now, coming back at the more application level, which is where people mostly talk about, I think in our project one of the grand vision is definitely to look at certain cognitive algorithms, such as, in our case, vision algorithms. So, as I said, one of the overarching goals of developing these components and eventually on a hardware platform, one of our goals is to try to see whether we can implement and map a real vision algorithm on top of this architecture. And this is some people refer to as computer vision. When I listen to talks from we are working with a neuroscientist from the Brain Institute at MIT, and they tell us that a large portion of our brain is apparently resources is dedicated towards vision processing. So it's computationally very intensive even for our human brain, and even to do a portion of that in today's CMOS technology, it takes enormous amount of power. It takes enormous amount of hardware resources. So what we are hoping is that these couple oscillator platform will provide us an alternate means to do that. Now, in the course of this grand vision, the kind of physics we will unravel in these kind of material systems, we call it these wacky oxide. The technical term is complex oxide.
Yeah.
The kind of circuit design techniques we will develop, the kind of algorithms, say, a nonlinear dynamical system theory that we will develop. I think all of these things at various levels could be applied to real-life biological problems. For example, what this particular professor at Glasgow is looking at, it might lead us to start thinking about, whether we can unravel, the cell signaling behavior. In fact, the other day, there's another area that I work in is in tunneling-based devices. These devices work based on quantum mechanical tunneling of electrons from one point to the other. And I find that apparently genetic mutation, some people think, there's a conjecture that is a result of a quantum mechanical tunneling process of a proton from one side to the other that messes up one of these base pairs and causes genetic mutation. So maybe at the very fundamental level, biology, physics, and computer science may actually converge at one point. I don't know whether that will be the case, but certainly that's a possibility.
Yeah, well, as a layman, I see that sure, all of this stuff connects in some way or other, and just in my mind, vibrations begin and maybe slow down, like you have, let's just take a theoretical construct of vibrations, very, very high vibrations beginning at the Planck scale, and very, very low level of vibrations begin and at the background hum of the universe. But that's just a layman's view of it, and somehow it all connects together in some sort of chain.
Absolutely. And I think you're mentioning very nicely this, we are traversing a huge length scale from a single molecule or even a proton to all the way to the cosmic, the background radiation effects. So, but the good news is that they're all oscillatory at some point, and it's for us to find the connection in this big pattern. I don't know if you heard that, Arijit, but
your turn in describing this oscillatory phenomena and the coupling phenomena of this and its link and its borrowing from not only biology at the macro scale, but at the molecular biology scale. Any thoughts on that?
Yes. So yeah, you're absolutely right. So the interesting thing about these oscillations is that we see it across all time scales and across all length scales. We see it in molecules, we see it in protons, we see it in the circadian rhythms of microscopic organisms, in human beings as well as in the universe through the background radiation and so on. So one of the things that I'd like to emphasize is that we are not necessarily trying to mimic the activity of the brain. So we are trying to get inspired by some of the computational processes that go on inside the brain, some of the basic nature of how the communication acts, the communication from one cell or one neuron to the other neuron works, and we are trying to emulate some of that using materials and devices that we know how to handle and how to engineer. So you're right in saying that many of the systems that we are studying will probably have very similar behavior, dynamical behavior, as some of the biological systems, and many of the basic physics or the basic mathematical formulations which guide how different kinds of oscillators couple in biological systems. The same mathematical tools and operations can also be used in our kind of systems, which are engineering systems, and we can get inspired by how nature works and try and emulate some of that in our systems as well. So the landscape of neuroscience, and when neuroscientists are looking at these kinds of oscillations, there is already a rich volume of work in neuroscience on oscillatory systems, and many of those prior research is essentially guiding us into how we can engineer the systems better, what kind of coupling mechanisms are needed. Once you couple systems, what kind of phase and frequency behavior should we expect? So it is also allowing us to perform new experiments. It's helping us in the design of experiments, in understanding our experiments, and at the same time put many of the systems together and apply the right algorithm on top of that hardware to realize some functional engineering blocks. So that's kind of our grand vision. And as Suman was mentioning, one of the grand challenges is to solve vision algorithms or vision problems. And the vision problem, again, I mean things like how do we recognize a person is something that is a non-trivial task in a computer. It's very energy intensive. It's also very computationally intensive. So it's not something which is very easily done. So if you can try and map some of those vision algorithms into hardware, particularly these kinds of oscillatory systems, that will be something that we are borrowing from nature, from biology, and at the same time we are using new materials or understanding of new engineering phenomenon to kind of emulate that aspect of nature into solving real life problems. So that's how I would look at it. But you're very right in saying that these kinds of oscillatory systems exist in cells, in protons, at the atomic scale, all the way up to the cosmic scales as well.
Yeah, and you know, biological systems are very plastic, self-adapting, and respond to the environment as the environment changes. And actually, you know, there seems to be an exchange of that. You know, the environment changes. Which comes first, the environment changes or the biological system which changes the environment? And where I'm going with this is one particular question that is very pertinent to this and relates to how it differentiates itself from digital technology. And well, I'll just cut to the chase. You know, as far as digital technology, the stuff we're using with today, it requires an enormous amount of software that is programming to to make this stuff run. And, well, how about this particular oscillation coupling-based computing system? Does that require any software? And I guess I'll throw it out to you, Suman. Does this require any particular software to make it run, or does it actually learn on its own and synchronize on its own?
That's a very good question. There is no easy answer to that. I think Hebbian learning process is one of the most distinguishing feature of biological systems. The fact that we human beings or any living organism look the way we are. Why do we have 2 ears and 1 nose and 2 eyes? I mean, definitely that has gone through many millions of years of evolution.
Yes.
But one of the most distinguishing feature of biological system, exactly as you pointed out, is the learning mechanism. So I'll try to answer this thing in 2 ways. The one is a short answer that we are aware of this learning mechanism that eventually we need to program into our hardware. So we're working on that. One thing that we are trying to do, we are doing a more brute force approach today. So as Arijit was describing to you, we have used our couple oscillators to do 2 types of tasks. One is what we call, what he described as pattern recognition, which is, let's say, I store an image of your face and memorize that pattern, and then I take a picture of your face and my face and present it to the oscillators. And at the same time, we invoke the stored image and present that to the oscillators as well. And if there is, depending on the degree of match, obviously in your case, your face versus the stored pattern, if there's a perfect match, the oscillators come to synchronization very quickly. Okay, boom. In my case, if I try to compare my face with your face, the oscillators take a long time to come into synchronization, and in this particular case, it would never come to synchronization. So that's the way we are trying to do this kind of facial recognition. But what's inherent to this thing is that I need some kind of a memory, whether it's a digital or analog memory, to store these memorized template patterns, right? So if I want these oscillators to really do a large number of tasks, I have to, let's say for face recognition, I have to store an entire database of faces, which means there's a prohibitive cost on the memory aspect of things, right? So that's interesting, but it's probably not as game-changing as we would want it to be.
Yeah.
The other part is related to before we go to just a face recognition software, there is other part to vision processing, which is called saliency. Turns out that saliency, or some people call it attention, when we are looking at an image, let's say there's a red Ferrari that's going across the street, I pretty much ignore what else is happening in the background, and I immediately sort of zone into that red Ferrari because, I like fast cars, and that red color is obviously helping. So what biologically, what we have evolved is that we have limited cognitive resources.
Yeah.
So if there's a animal chasing me, I need to run quickly. Yeah. I need to focus on the animal and get out of its way in order to survive. So survival and evolution adaptation has made our brain extremely efficient in trying to sort of do these attention or saliency detection very efficient. One of the things that we are finding with these couple oscillators is that this nature of this dynamic synchronization, when we compare with traditional architecture, it does this saliency very well. It very quickly, we use an algorithm called center surround difference, and it can very quickly figure out what's the most salient features of a particular image. And I'm talking about static images, and we're going to go and look at moving frames and so on and so forth. But what we want to do going forward is that if I show a particular image over and over and over again to this particular couple oscillator system, over time, can we end up in a situation where these couple example, oscillators will synchronize faster and faster and faster and more efficiently because there is some kind of inherent, well, I've seen this before. I knew what it is. And that part is a little bit more complicated because of the simple reason that you're looking at not only the computation aspect, but you're also looking at the long-term, short-term memory aspect of things. And that's something that is not quite trivial. Having said that, I should mention to you the work that's going on in some other groups around the world related to memristors, or what people call programmable synapses. And we are part of in our center. We have folks from Stanford who are working on particularly this aspect of the Hebbian learning process. So through experience, you can train the network so that when you present it with a situation that it has encountered before, it does a better job of recognizing that event or recognizing that feature. So it's possible. It's not quite obvious, but clearly the learning mechanism is probably the most complex thing to tackle in an artificial hardware system.
It's fascinating in the way that you describe how this particular system works reminds me. And I'm trying to push it as a bio geek, and I've studied neuroanatomy, and I'm trying to correlate this with, and it actually correlates in my mind beautifully just off the cuff, is that, well, on the bottom layer, let's say, and I'm just going to use a quick analogy because we're running out of time, but let's say you have the spinal chordal mechanism that has various sort of pre-programmed reflex arcs, and the spinal cord goes up to, of course, connects to the the lower brain, the pons and the medulla and the midbrain, and somewhere above that, let's say in the mesolimbic system, you get, and of course the sensory system that integrates into that, you get a certain phenomenon that are able to catch exactly what you described, motion detection better, and when you said earlier in the show that this particular system would be quite apt to sit on top of digital technology as an adjunct, and I was wondering if you could maybe speak to that in the final couple of minutes that we have left. And I guess I'm going to go knock it. Let's see. Arijit, what do you think about that?
Yeah, I think that's a fascinating example. I think you're very right. I think this entire notion of being able to compute or recognize something very hierarchically and different layers of the brain has also inspired some other computational models like hierarchical temporal memory and so on. And many of the basic paradigms of computation are very similar to how we process information in the brain. And the whole notion that we have memory and compute kind of fused together in the brain is something that these oscillatory systems also seem to exhibit. So again, long story short, if you think about any kind of information processing as a hierarchical process, we see that as these synchronous systems slowly synchronize over time, they first kind of zone in on the coarser features, and they finally zone in on the finer features, and then they finally give you the response that you would want. So again, in a very similar fashion that you mentioned, like in the brain, we can have different layers of the hierarchy, and different layers of the hierarchy will give you different levels or resolutions of pattern matching or template matching, whatever the task is, and they slowly converge into a final solution over a period of time. And this is exactly what these oscillatory systems also tend to behave when they are correctly stimulated by the right input patterns, and they are correctly read. Because the other important engineering aspect of the whole thing is that if you let these oscillatory systems evolve over time, you have to be able to read their responses. You have to be able to identify the phase differences, phase patterns, and so on. So how do you do that is a very big question. It's still an open-ended question, and this is something that we, like many other groups, are also researching. We're trying to identify how to stimulate these large systems, how to observe these large systems, and also make sense of how these systems evolve over time, because they inherently can give you very interesting solutions to well-known problems, but we have to be able to engineer the right solutions out of them by providing the appropriate read-write circuitry and so on. Just like it happens in the brain. So the brain controls the muscles and so on. So similarly, all these oscillatory systems need to control output devices, which we will connect to them, and hopefully we can get a whole system working and produce associative computing or template matching computing that we are thinking of.
Beautiful, beautiful. And one final question to Dr. Suman Datta is that, well, and I'm going to mention, just for the sake of brevity and time, that this consumes remarkably a lot lower power than digital technology because of all the infrastructure involved with digital technology and Moore's law and, well, heating issues and all that. But that aside, what do you see with regard, you're at the beginning, you're at the forefront, and I guess, and this is a very difficult question to answer because, you know, how do you know how much time it's going to take to scale up this system? But I'm just going to go ahead and throw it out to you, Suman, anyway. Any thoughts on transition time and scalability and applicability of this?
Sure. I'll quickly, because we're running out of time. So my quick answer would be, this is exactly what we're trying to do. Our first paper on this subject that came out, we have two huge oscillators, huge in the sense of it's 2 micrometer by 2 micrometer. The world I live in, 2 micrometer is like 1/1,000,000th of a meter, but it's still huge because most of the stuff that we do in today's digital electronics is more like tenths of nanometers, and we are going down to single nanometer level. So from that standpoint, I look at we're about tens of generations behind where today's digital technology is. Okay. Having said that, that's today. We are aggressively going after dimensional scaling of these oxide, these wacky oxide-based devices. Our roadmap shows that, our current roadmap is that we want to get down to about several tenths of nanometers, 50 nanometers, which is like a billionth of a meter in the next year or so. We will also, as we try to make the individual devices smaller, we will have an opportunity to connect now larger number of oscillators to form an array. Right now we are at 2 to 3 oscillator level. We'll be continuing to work with the Georgia Tech group, trying to understand the experimental results that we collect on larger arrays. It's hard to say. I think one of the things I want to point out is that just like no humans are created alike, no 2 oscillators are created alike. One of the biggest challenges in demonstrating a system-level functionality is variation and device-to-device fluctuation, and how do we do how they would affect this nonlinear dynamics is a completely open question. Nobody till today has successfully made anything more than 7 or 8 oscillators that are coupled together. So we are in uncharted territory right now going forward. But that's the advantage and also the curse of being at the forefront. But we are quite excited. Well, as far as technology insertion, I think I have a favorite saying. I worked at Intel for 8 years, and we did a lot of crazy stuff, and many of them went into product. Arijit was at Intel with me as well, and I think my favorite quote is, the best way to predict the future is to invent it. So progress, and we'll see how far we can go. Right now, I don't think that there's any company that's really counting on would tell you that, okay, we have a couple oscillator-based associative processor in our roadmap or a product. But I think this is an exciting field. We are talking to Intel, Microsoft Research, and so on and so forth. So if we get these big the companies to keep a tab on this thing, and we continue to show more advancement, and there are other groups that are working on this thing, I am positive that we'll see something useful come out of this.
Well, fantastic. There's a lot of hope in this, and I wish you both the best of luck. And sometime in the future, we're going to have to do a follow-up on the progress. And Dr. Arijit Raychowdhury and Dr. Suman Datta, I want to thank you very much for being on, and really cool stuff. And keep up the good work, and let me know how things progress.
Thank you so much.
Thanks
Pleasure
so much.
to be here.
Thanks for having me.
Great to have you on, and we'll see you on the flip side. Thanks.
Thank you.